A Siamese network is where you have two identical parallel convolutional neural networks structured so the network can learn similarity by optimizing a rank loss function, rather than classifying or detecting something. A common application of this would be a security entrance, where you have images of all of your employees, and to gain entry, their face has to have a high enough similarity to what the model has learned of their face based on an acceptable threshold. Let's break this down into the main components. First, we have the data, which is separated into one folder for each class, but we create triplets of data to train the model. This triplet consists of an anchor image, a positive image, and a negative image, where the anchor and positive must have the same class and the negative must be a different class. Second, we have the model, where feature extraction is performed, and an embedding is made out of the image. Next, we have a contrastive loss function to help the model learn to prioritize parameters that create embeddings that produce a smaller distance between similar class types and a larger distance between different class types. Next, we have the training module, where we use different hyperparameters, like the number of epochs, learning rate, and distance threshold, to train the model. Finally, we have the plotting and data analysis, so we can make better choices of how we train the network. Let's look at the high-level view of how this translates to the coding architecture. I like to keep functionality separate for each class, so the main function creates a model trainer class, which can train or evaluate. When training, it iterates through each epoch, feeding the data through the model, and uses a loss function to optimize the embedding parameters. This highlights that the model trainer has both the Siamese Network class, which defines the model for feature extraction and embedding creation, and is inherited from the parent class, and n.module from PyTorch. And it has a triplet loss class, which defines the loss function used while training. I have a data reader class inherited from PyTorch's utils dataset, which handles reading in and arranging the data that gets sent through the model or the evaluator. The evaluator has a visualizer class, which helps create evaluation plots. I also have a logger to write the progress and results to a results.txt file, and save useful plots to a certain directory within a runs folder for that run. I made this a singleton, which is a design pattern that allows more than one source to use the same instance, so there's no fighting over the right function, though I do lock it down to avoid multiple threads from accessing it at the same time. Now let's look at the training. First, we have the data. I separated my data into Nick, Nelson, and empty because I want to be able to easily plot the difference between the three, even though I'm trying to detect Nick or toddler versus the other two. When I pass the data through, I'm sending it in triplets, one anchor, one positive example, and one negative example. Actually, a lot of thought in industry has gone into choosing an anchor. Choosing a hard anchor means the embedding distance between the negative example and the anchor is not very large, or in human terms, it's hard for the model to tell the difference between the negative and the anchor. If you choose this route, the model might converge more quickly, and the model can sharpen the decision boundary between classes, but there's also risk of overfitting and a noisy gradient. Choosing a medium anchor is not as difficult as a hard anchor at determining the difference, though there is still a reasonable challenge. When you use a medium anchor, there's a balance between easy and hard, so it helps avoid negatives of hard like overfitting and noisy gradient, but it still helps prompt the model to learn a broader variety of cases. But it may be slower to converge. If using a soft anchor, it's relatively easy for the model to distinguish between the anchor and the negative image, and it makes it easy for the model to find patterns and relationships in the data and avoid the risk of noisy gradients or unstable training. Though if only using soft anchors, the model might become too simplistic and fail to generalize to harder examples. Next, for the model, I'm using ResNet, the residual neural network for feature extraction. I started with a series of convolutions, ReLU, max pooling, and batch normalization, but I moved to using ResNet as it was a better feature extractor. It uses skip connections to jump over layers in the network so it can learn with great depth. Next, I'm using a triplet contrastive loss function which optimizes to have a distance between similar types and different types be of at least a certain margin parameter. Here's where we define the similarity metric. I varied between the Euclidean distance, which is just the distance between the 2 points, and the cosine similarity function, which measures the similarity between the cosine of the angle between the vectors, or the dot product of the vectors divided by the product of their lengths. This only depends on the angle of the vectors, not on their magnitude. So in the training, I iterate over my epochs, feed my triplet datasets through the model, and allow the model to update its parameters to improve performance based on the triplet loss in the atom optimizer, printing the updated loss at each epoch, and I ultimately save off the model in the end. I also have an evaluation path to send new data through the model, so on each training iteration, I send the validation data through the trained model to see how it performs. The test data I'm saving until the end to be able to compare it to the other models. And because we're not detecting a bounding box, we don't have to consider the IOU, but we're still using the average precision for toddler class. If you'd like to see where I implement this algorithm and others, check out the bathroom terror detector, and don't forget to subscribe for more.